In the 17th century, Isaac Newton demonstrated that a seemingly uniform beam of white light is actually a tightly packed composite of multiple distinct wavelengths. When these wavelengths travel through the air and cross a boundary into a denser medium, like water or glass, they slow down. This change in speed causes the path of the light to bend, a physical process known as refraction. This captures the physical reality of that process. A standard geometric shape like this glass prism forces incoming white light to separate into a visible spectrum. This separation occurs because the glass does not slow all light down equally. Each specific color, or wavelength, experiences slightly different drag, meaning it bends at a slightly different angle. This macroscopic separation is a strict physical process, governed by predictable rules. To understand exactly how it operates, we need a precise mathematical framework. That framework begins with the refractive index, represented by the variable n. This is a simple ratio. It compares the baseline speed of light in a vacuum to its slower speed inside a specific material. This illustrates Snell's law, the empirical equation predicting the exact angle light bends when crossing media boundaries. Under Cauchy's principle, shorter blue wavelengths have a higher refractive index than red. Moving slower, they bend sharper. But there is a limitation here. Snell's law is purely an empirical observation. It perfectly predicts exactly how the light bends, but it offers absolutely no explanation as to why it chooses that specific angle. To understand optics, we have to look past surface boundary rules and analyze the entire trajectory. We find light follows a singular, overarching physical optimization. Consider a light source originating in a dense medium, like water, pointing upward into a lighter medium, like air. As we increase the angle of incidence, the refracted angle increases even faster, bending away from the vertical normal. Eventually, we reach the critical angle. This is the limit where the refracted angle hits exactly 90 degrees, grazing the boundary surface. If the angle of incidence exceeds this, refraction becomes impossible, and the light reflects entirely back. Total internal reflection demonstrates that the boundary between materials acts as a mathematical wall, enforcing strict geometric rules on light's behavior. To uncover the physical cause driving these rules, we rely on pioneering physicists who recognized we needed to shift how we frame the problem entirely. That shift traces back to Pierre de Fermat, who proposed a radical hypothesis in the 17th century regarding the paths that light chooses. Fermat defined the principle of least time. He argued that light will always traverse the specific path between 2 points that requires the absolutely shortest duration. He did not say the shortest distance. A straight line is only the fastest route when the medium it travels through is perfectly uniform. If Fermat is correct, the seemingly arbitrary angles of Snell's law are actually the geometric side effects of a universal optimization problem based on speed. We test Fermat's principle directly. Point A is in a fast medium, like air, and point B in a slower medium, glass. We calculate the travel time of a perfectly straight line connecting the two. This direct route is highly inefficient. By going straight, the light spends a disproportionate amount of time dragging through the slow glass medium. We can propose a faster route by drastically minimizing the distance traveled inside the slow glass. We stretch the path in the air and drop almost vertically to point B. This introduces a steep trade-off. Time in the glass is minimized, but distance in the air increases so much that the total time is worse. There is a singular, mathematically perfect point on the boundary that perfectly balances the extra distance in the air against the time saved in the glass. When we calculate the geometry of this exact optimal point, the resulting angle is mathematically identical to the angle predicted by Snell's law. This textbook page documents the formal geometric proof of least time. The math demonstrates exactly how velocity differences dictate the path. The light is not blindly following a surface rule. It is actively solving a complex calculus problem to find the path of least time. Fermat's principle also governs continuous environments with shifting temperatures, where refractive properties change gradually rather than at a single interface. Look at the puddle of water on this long road. That is a mirage. Light from the sky curves upward before hitting the hot asphalt, because the hotter, thinner air near the road allows it to travel faster. Curving through that fast air minimizes its total time to your eye. We can also engineer tools to manipulate this optimization. A converging lens relies entirely on the principle of least time. The physical mechanism of the lens is designed to control speed. The thick glass in the center intentionally slows down the shortest, direct route. This delay compensates perfectly for the longer distance traveled by the outer rays passing through the thin edges. Because the times are equalized, every single ray hits the focal point at the exact same millisecond. A lens is a constant time machine explicitly engineered to equalize multiple optimum paths. All of this raises a seemingly paradoxical question. How does a photon know which path is the fastest before it even begins its journey? This blackboard details the quantum electrodynamics explanation for macroscopic optics, relying on wave theory and probability. At a quantum level, a photon explores all possible paths between 2 points simultaneously. Each potential route is represented by a small rotating phase vector, an arrow indicating its timing. When paths take vastly different amounts of time, their phase arrows point in random opposite directions. Through destructive interference, these extreme paths mathematically cancel each other out. Only the paths clustered tightly around the least time route take nearly the exact same duration. Because their times match, their phase arrows point in the same direction, accumulating probability through constructive interference. The strict, precise laws of macroscopic optics, prisms, lenses, and Snell's law are merely the mathematical survivors of a quantum probability calculation, revealing that nature is always perfectly optimizing for time.